So moving forward, after we solve for the flow factor of top and bottom, we will use the entrainment correlation for C plates, assuming that our plate spacing will be at 0.60 meters. So the red line indicates top at 0.09 and the purple for the bottom is at 0.06. So after we obtain the KV for top and bottom, we can now solve for the maximum volumetric flow rate or the Vmax for the top and bottom of the column as well. So here is the Vmax top. It's equals to KV top, uh, quantity of theta over 20 to the quantity of exponential of 0, 0.2, then square root of the density of liquid in the top minus the density of vapor at the top over the density of vapor of the top. So getting your values and then inputting it over here, then we will have the Vmax of top, which is 0.16 or 0.17 meter per second. So for the bottom, pretty much the same. K then the theta over with the over 20 and 0.2 at the exponent. But the difference is the here, uh, rather, yeah, the only difference is that instead of getting the density from the top, we will use the bottom ones. So our Vmax bottom is 0.0967 meters per second. Now we are going to solve for the V design top. So we are going to assume for 80% flooding multiplied by the Vmax from the top. So we have our V design top is equals to 0.1336 meters per second. And for the bottom naman, we will use flooding as well. Assume 80% flooding multiplied by the Vmax at the bottom. We will get 0.10 or 0.11 meters per second. So calculation of volumetric flow rates. We have the top. We assume 41,900 over the PV of top and then divided by 3,600 seconds. Same as for the bottom as well. So the difference is the PV on top and the PV on the bottom. And then next is the area of the column. So the top is equals to the VFR of the top over the V design top. So our top is equals to 3.8118 meters squared. So for the bottom is VFR as well, but for the bottom, then over the V design bottom. So our bottom is 3.71 meter per second. No, not meter per second, sorry. Meter squared. So column in the cross-sectional area. So top is equals to the area of the column, then percentage of the flooding. I over the percentage of the floodings as well as for the bottom as well. But so you get the area of the column. So we have 3.8 and then we are going to divide it with the 80% of the flooding. So we have for the top we have 4.77 and as for the bottom we have 3.71 and then divided with the flooding is 4.63.
Moving forward, to calculate the diameter of the column, we need to find the average of the diameter at the top and bottom. Using the formula of square root of 4 times the column cross-sectional area divided by pi. By substituting the values, we get the diameter at the top as 2.47 meters and the diameter at the bottom is 2.43 meters. In distillation column design, using the same diameter for the top-bottom sections can be practical and cost-effective, but it may not always be the most efficient choice. The decision depends on several factors, including the first one is vapor and liquid flow rates. The flow rates vary along the height of the column. Typically, vapor flow rate decreases towards the top of the column due to condensation, while the liquid flow rate increases due to accumulation from the chase or packing. This variation can influence the required column diameter at different heights. The second One is pressure drop consideration. A uniform diameter might lead to a higher pressure drop, especially if the vapor velocity is high at a certain section. This can affect the separation efficiency and energy. And for the area of the column, we use the formula of pi times the diameter divided by 2 all squared and obtain a value of 4.71 square meters. Alright, now we'll be calculating the area of a downcomer. As you know, the downcomer area is typically 12% of the area of the column. First, let's start with a given area of the column. We previously calculated it as 4.71 square meters, and the formula to find the area of the downcomer is straightforward. We simply take 12% of the column's area. Mathematically, this is represented as area of the downcomer equals 12% of area of the column, which is 4.71. When we do the calculation, we get the area of the downcomer of 0.5647 square meters. For the net area, we simply subtract the area of the downcomer from the area of the column, resulting in a value of 4.14 square meters. The active area is calculated as the area of the column minus twice the area of the downcomer, which give us 3.58 square meters. To determine the whole area, we take 10% of the active area, which is 3.58 square meters, resulting in 0.36 square meters. We assume that the whole area diameter and thickness are both 5 mm. The area of a single hole is calculated using the formula of 5 times the radius squared, or half of the diameter. This gives us a single hole area of 1.96 times 10 to the power of negative 5 square meters. To find the number of holes per plate, we use the formula of n equals total hole area all over area of one hole. By substituting the values, we find that there are 18,220 holes per plate.
In the realm of equipment design and CAD visualization, creating intricate designs of column internals such as trays and packing is essential for optimizing distillation efficiency. Utilizing advanced CAD tools, we generate precise 2D designs that provide a clear top view of the column, which has a diameter of 2,447.8 mm. This design includes a downcomer hole with a chord length of 2,173 mm and a segment height of 665 mm. These specific dimensions ensure proper liquid distribution and vapor flow, which are critical for effective separation within the column. In the detailed 2D design of the tray plate, we focus on critical specifications to ensure optimal performance. Each hole on the tray plate has an area of 1.96 times 10 to the power of negative 5 square meters and a diameter of 5 millimeters, with a total of 18,220 holes distributed across the plate. The plate itself has a thickness of 5 millimeters. Additionally, the downcomer area is 0.5647 square meters, complemented by a downcomer panel measuring zero point 0.3 meters. These precise details are crucial for ensuring effective liquid and vapor distribution within the distillation column, thereby enhancing the overall separation efficiency. In our 3D design visualization, we bring the tray and its intricate components to life with detailed accuracy. The same parameters and measurements mentioned in the previous slide are applied here. By leveraging advanced 3D CAD tools, we can simulate real-world conditions, allowing for a thorough analysis and optimization of columns' performance. This design is aimed at enhancing the overall efficiency of the distillation process, ensuring optimal separation and minimizing potential issues such as flooding or whipping. The precise measurements and robust construction of the tray plate contribute significantly to the distillation column's performance, reflecting careful consideration of both operational and structural requirements. In a distillation column, the top and bottom cups are typically designed with the same height and diameter for several practical reasons. The consistent cap height of 1223.9 millimeter and the column diameter of 2447.8 millimeter ensures uniform structural integrity and mechanical stability, simplifying the manufacturing and assembly process. This uniformity allows for easier installation and maintenance, as identical components can be used for both ends of the column, reducing the need for multiple designs and specialized parts. Additionally, the same cross-sectional area of 4.77 meters squared of both ends ensures consistent flow dynamics, minimizing pressure drops and ensuring efficient separation processes. By maintaining this dimension, the column can handle similar flow rates at the top and bottom, which is crucial for the even distribution of vapor and liquid phases, thereby optimizing the distillation efficiency and performance. The 2D and 3D design details of the tray plate for the distillation column reveal that the tray spacing is precisely 600 mm. The column itself features a thickness of 19.93 mm and a diameter of 2447.8 mm. In the 2D view, the tray plates are arranged in a manner that maximizes the efficiency of the distillation process with clear indication of the spacing and alignment. The 3D model provides a comprehensive visualization showing the column's cylindrical structure and the spatial arrangement of the trays within. This detailed design ensures optimal flow and separation within the column, adhering to the specified dimensions for effective operation.
In our 3D design visualization of the distillation column, we meticulously model both the column shell and the tray plates inside. This detailed 3D representation includes the column structural dimensions and the precise layout of the tray plates, ensuring accurate placement and spacing. The visualization highlights the interaction between the column shell and the internals, demonstrating how the tray plates, each with thousands of strategically placed holes, facilitate efficient liquid and vapor distribution. In our 2D design of the distillation column, we detailed the overall structure and configuration. The column consists of 21 stages in total, with 13 stages dedicated to the stripping section and 8 stages to the enriching section. The height of the column is 15,400 millimeters, and it has a diameter of 2,447.8 millimeters. The column's thickness is specified at 19.93 millimeters. This precise 2D representation provides a clear and accurate overview of the column's key dimension and stage distribution, ensuring a comprehensive understanding of its design and functionality.
At this part, I will be illustrating the key equipment's auxiliaries in a distillation column, including the reboiler, condenser, pumps, reflux drum, and more. Auxiliary equipment plays a crucial role in the efficient operation of a distillation column. This component ensures the proper separation of mixtures and the overall functionality of the system. Each component of the distillation column plays a vital role in the separation process. The feed introduces the mixture for separation and balances the mass and energy within the system. The rectification section focuses on enriching the vapor in volatile components. The stripping section focuses on stripping volatile components from the descending liquid, concentrating less volatile components in the bottom's product. The reflux improves separation efficiency and maintains temperature control. Together, these components work in harmony to achieve the desired separation, allowing for the efficient and economical production of high purity products in a distillation process.